And now we move to our second talk in this section. It's again a speaker from the United States. So it's my pleasure to invite Jorn Venderbos from Drexel University. Please go ahead, please.
Okay, great. Thank you. So everyone can hear me?
Yeah. Yeah.
Okay, thank you. Well, thank you very much to the organizers for having me in this very nice, interesting, and beautiful workshop. It's nice to see even a number of old friends, both in the audience and online. So I'll talk about altermagnets and topology and take a perspective that starts from minimal models. So in that sense, this is a talk that is very much in the same philosophy as the talk yesterday by Daniel Achterberg, which is that there is a lot that can be learned, a lot of insight can be gained by considering and examining altermagnets using minimal models. So in a sense, that is reducing the essence of the electronic structure down to its smallest working part in order to address and answer some broader questions. And Daniel had a number of very interesting and important questions on one of his slides that you might want to think about, such as, and he talked about that, the role of spin-rotary coupling. And in this talk, I'll focus on another aspect, which is the role and connection of topology with altermagnetism. All right, so with that, let me just briefly acknowledge a number of important people that I've worked with. So on the left is, actually, I guess, I hope you can all see my my pointer here. So the work that I'll be talking about was primarily done with Rafa Fernandez, Daniel, who is now at Yale, was my postdoc, and with my student, Beryl. And these are the right-hand side, some collaborators on the experimental side with in areas of unconventional magnetism. So the talk will basically have two parts. In the first, I'll talk about altermagnetism and its connection to topology from the perspective of symmetries, energy bands, and the structure of the Hilbert space, topology of the Hilbert space. And then in the second part, I'll focus on responses, to external fields, and I'll focus that on, in this case, piezomagnetism in the context of altermagnets, and try to point out how you can view that through the lens of topology as well. All right, so my starting point is what I think one might regard as one of the simplest non-trivial models that support altermagnetism. It certainly is one of the simplest non-trivial models that manifests both altermagnetism and topology, and that's shown here on the left, the Lieb lattice model. Okay, so that has two magnetic sublattices shown here in red and blue. Now these are equivalent magnetic sites, but this is just, we would like to consider a nail state on this lattice, and so you should think of this as up and down. Okay, and the key point is that there is a non-magnetic site here indicated in white, such that the two magnetic sites see different local crystallographic environment. Okay, and so that means that the magnetic sites are exchanged by a fourfold rotation, but not by inversion, and certainly not by translation. Okay, and if you examine all the symmetries that exchange the two magnetic sublattices, then once you consider a nail state on this lattice, meaning, let's say, up on one sublattice, down on the other, then it's simple to deduce that this would be a model for a dx squared minus y squared altermagnet. So d-wave altermagnet with that particular symmetry. Okay, and so what we would like to do is construct a minimal model that accurately captures all of the key features that would be necessary to understand the electronic structure. And that's a broader philosophy here that I'm just applying. And here's the simplest model that you can write down. So Hamiltonian is here. It includes a nearest neighbor hopping, nearest neighbor coupling, as you would expect. But an important piece here is the anisotropic D-wave hopping. So if you look here on the left-hand side on the lattice, and you consider, for instance, the blue side, then there is a hopping with different sign going up and going laterally, and that is flipped for the other lattice because of the particular symmetries and the fourfold rotation that maps them into each other. Okay, so this is a model that takes into account the two sublattices and the two spins. And so the last part here is just the nail state with anti-aligned spins. Okay, and the combination of these two terms makes it an altermagnet. All right, so if you look at the energy bands, if you plot them, then you obtain what is shown here. Okay, so in blue, let's say, is spin down, and red is spin up. And if you look at this at the splitting here that you see at M, then that is proportional to the nail vector, and the splitting that you see here at the X points between the up and down bands, that is caused by this anisotropic hopping that gives rise to this D-wave spin splitting. Now, one feature that is that's kind of interesting here. So first of all, you do see from M to gamma a crossing of bands of opposite spin. That's what you would expect for a dx squared minus y squared altermagnet, right? That's where the nodes of the form factor are. But there's an additional feature, namely a crossing in between x and m and in between x and m prime, and that realizes a Dirac crossing. Okay, and that is something that emerges immediately once you include the effect of magnetic order in this model. So on the left-hand side here is shown the model with no nail vector, no magnetic order, so the non-magnetic phase. And as you include the effect of magnetic order, you'll see that on the mirror lines, these Dirac crossings occur. And if you want to understand why they're there, then you can consider on these mirror lines the mirror eigenvalues of the bands that cross, and you realize that these are opposite mirror eigenvalues, and therefore these are Dirac crossings that are symmetry protected on the mirror lines. There's a broader way to understand this, namely from the perspective of splitting a quadratic band crossing, and that's really where the essence of topology comes in. So once again, on the left-hand side, in the non-magnetic phase, so no nail order, there is a quadratic band crossing at the M point. Okay, and what happens when you include magnetic order is that this quadratic band crossing splits into two Dirac points, and that happens for each spin species. Okay, so for spin up, for instance, they move in this direction here from left to right, and up and down for spin down. Okay, so here this is a schematic picture of how that happens, and so this is an example of Dirac points of valleys, a valley degree of freedom that is spin valley locked, rather than but in this case not caused by spin-orbit coupling, but by the altermagnetic order. And so the idea of a quadratic band crossing splitting into Dirac points that was pointed out earlier in this paper here. And so by drawing from that, we can actually write down a fairly simple continuum model for altermagnets and topology. So if one is looking for a very simple model for that, then this would be it. Okay, kind of the Dirac model for graphene, but for altermagnets, if one wants to push the limit a little bit. So let me then consider the effect of spin-orbit coupling. What I said until now was all without the effect of spin-orbit coupling. So let me introduce that and see what happens. Okay, so once you include that, then you have to realize that now the direction of the nail vector matters. Previously, it did not, and so there's two cases that we should distinguish. On the left-hand side is a picture of a nail vector pointing in the z direction. And on the right-hand side is the two possibilities for having the nil vector point in the plane. Okay, so these we'll consider these separately. And one aspect that was pointed out in this paper by Paul McClarty and others is that if it's in the plane, then there's also a direct coupling to an overall magnetization. But let me first consider the case where the nil vector is in the z direction, and then the altermagnetic state retains a C4T symmetry. So I believe that that's typically referred to as a pure altermagnet. And importantly, it also has an MZ mirror symmetry. So the plane of the system remains a mirror plane. And in this case of easy access anisotropy, if you include the effective spin-out coupling, and so that's shown here in the right, there's a term you can include that very much has the flavor of the Kane-Meili spin-out coupling in graphene, but now on this Lieb lattice. And if you include that, then what you notice is that the Dirac points acquire a gap. If you examine the nature of the bands, then you find that these bands have a Chern number, but the spin up and the spin down bands have opposite Chern number. Okay, so that and these are related because they are related by the mirror symmetry. The topological characteristic of this system is a mirror Chern number. Okay, so in this case, I'm showing an example where there's an actual energy gap. If you imagine that you are in the gapped phase, then this is a mirror Chern insulator. Now, you can ask the question, well, is there a way to get out of that phase? Is there a transition to maybe a trivial phase? And the answer is yes. So what is shown here is that you go through a topological transition as you increase the strength of the Nail order parameter. And that's maybe something that you might expect, because eventually, if that becomes very large, you should be in a trivial product state. So on the left-hand side is the mirror Chern insulator. Then at a particular critical strength for the Nail order parameter, you go through a Dirac fermion mass inversion transition for one spin speed at the x point, for the other one at the x prime point. So again, this idea of spin valley locked spin valley locking at the two valleys, and then you're in the trivial phase. In the other case of in-plane anisotropy, as I said, you have to include the effect of an overall magnetization as well. So here I just really want to point out the basic point, which is that there's two possible solutions for the nil vector. In one case, when it points along one of the principal axes, then the induced magnetization is also in the same direction. And in that case, you preserve a perpendicular mirror, and that's why this crossing here is still stable. In the other case, here the nil vector points along the diagonal. There is a perpendicular magnetization that is induced due to the structure of this coupling, and you see that the Dirac points that were there without spin-over coupling are now gapped. Okay, and it all depends on the breaking or preserving of a mirror symmetry. Now, this is in two dimensions. We also considered an example in 3 dimensions. Again, topology in the context of minimal models. I will not dwell on that for too long. I'll just basically mention the main point is that you could consider a model for the class of rutile altermagnets. Examples are this manganese fluoride and ruthenium oxide, although in practice, there are questions about the magnetism, but for the moment, let's just consider the question of what model would describe it. And then the main point is that in the case of a nail state in a model like this, you can write down all the allowed couplings and the relevant ones. If the nail order parameter points in the z direction, then again you preserve an MZ mirror, and then you can look at what the bands do in the kz equals pi mirror plane, and you see again that there's a crossing, right? If you're in the limit of no spin-over coupling, these are really uh, um, spin projected, there's a crossing which realizes a while line node on this mirror plane. Again, that is not a crossing or a degeneracy that is imposed by simply the symmetry of the altermagnetic state. In this case, it's dxy, but that appears as an additional crossing protected by mirror symmetries. Okay, so that's an example of this in 3 dimensions. So I'll try to make my transition to discussing responses in the context of these models. And in order to do so, I want to introduce 2 more minimal models for altermagnets in 2 dimensions. Okay, just as toy models for realizing a different kind of altermagnet, different symmetry. Okay, and one is shown here on the left-hand side. This is not a model I came up with. I don't see the citation here, but anyways, this is a minimal model in 2 dimensions for a dxy altermagnet on a tetragonal lattice. And if you look at the symmetries carefully, then it's essentially a 2D version, or you can think about it as a 2D version of this 3D rutile lattice model. So a lot of that carries over. So this is a dxy altermagnet. The fourfold rotation here and the twofold rotation exchange the sublattices. Then there's another model which realizes a G-wave altermagnet, also on essentially a square lattice or tetragonal lattice, and that is shown here on the left. And the way you might think about that is as magnetic sites that sit in some kind of octahedral cage. And when the octahedra rotate, then that creates this 2 sublattice structure that is shown here. And so this is a 2D version of octahedral rotations that are fairly common in perovskite materials. And in this case, the magnetic sites are exchanged by all in-plane twofold rotations, but not by the fourfold rotation. Okay, so this is, if you examine what symmetries exchange the sublattices, then you notice that this is a G-wave altermagnets with this particular symmetry signature. And so these are all models that can be nicely captured by a general minimal model Hamiltonian for 2D pure altermagnets. So that's something that that I will be considering in this talk. So pure altermagnets. I'm always going to assume that the nil vector is for the rest of this talk is perpendicular to the plane. And so again, there is this is, by the way, a formulation that's very similar in spirit and in appearance to the work of Daniel Achterberg in his paper. There's a piece that represents the anisotropic crystalline environment that you want to put in. There's a spin-up coupling term here, okay, and precisely because of the direction of the nail vector, basically because of the 2D symmetry, it has this sigma z, and here I'm choosing nail vector in the z direction. Okay, and so these 2 functions here, they are specific to the lattices considered. The rest is fairly generic. And then one thing that I want to observe here is that the Hamiltonian is diagonal in spin space. That's because of the choice of the nil vector and the presence of the mirror plane. And so there's a convenient form of this Hamiltonian as an expansion in Pauli matrices that I'm going to exploit now that I'm going to talk about responses. Okay, so this is part 2 of the talk. We'll see how much time I have to go through all of it, but at least I'll probably be able to convey the gist. So the response that I want to focus on is the piezomagnetic effect. And so this is something that has been said before, or has been observed by a number of different groups, is that pure D-wave altermagnets are natural candidates for piezomagnetism. That is to say, a magnetization induced by an applied strain. And so that phenomenon can be captured here in terms of this response equation, linear response equation, where the magnetization is linearly proportional to the applied strain, and this linear coupling here is the piezomagnetic tensor. Okay, so M is magnetization, epsilon JK here is the strain tensor, and this is just a schematic picture of that. Now, as I said, a number of people have made this observation that that by the nature of altermagnetism and their order, they're natural candidates. So here, let me show you one example of work of others that have demonstrated this effect in the context of the Lieb lattice model that I showed. So this is work that my collaborator Rafael Fernandez was involved in. So you can take that Lieb lattice model and include strain through additional anisotropic hoppings that break the symmetry, and then just compute the magnetization in this way. And this is what they found. This is a function of chemical potential, and here is the computed magnetization divided by the strength of the strain. And the thing that I want to point out here is that this response vanishes for an insulating pure altermagnet. So these are values of the chemical potential where, for the choice of the parameters, you have an insulating altermagnet. So this and there this vanishes. And there's reasons for why that is the case. But what I want to focus on is not the spin magnetization, but the orbital magnetization and its response to applied strain in these systems. Okay, so this is putting the spotlight on an orbital piezomagnetic effect. And so strain also can give rise to that, right? And so orbital magnetization is something that is a little bit similar to electric polarization. And if you want to examine that in microscopic models, then you have to rely on the modern theory of orbital magnetization. And so, this is how how polarization is calculated. This is how orbital magnetization is calculated. And the modern theory tells us that eventually you can convert that to a momentum space integral over this object here, which has the eigenstates, derivatives of the eigenstates, and the energies. Okay, that's the key content of the modern theory. And so this is maybe a little bit of a technical slide, but it sets me up for applying that to the class of models that I'm interested in. So you can include the effective strain in this general formulation of these 2D pure altermagnets. Okay, so the full Hamiltonian then has a piece here on the left that represents the pure altermagnet, and then you include the effective strain through some parameter that is the strain field and some form of the strain perturbation. You can write this again in a more compact form by realizing that the two spin sectors decouple, and then there's some function psi here and a vector h of k, for each spin sector. And then what you can show is in this formulation is that this general expression for the orbital magnetization takes a fairly nice compact form, which emphasizes the role that topology plays for such a response. Okay, because this piece here that you had this piece of the integrand that you have to integrate over is essentially the Berry curvature. Okay, and so here's a result for the Lieb lattice model calculating the orbital magnetization. On the left is just a show of the bands in the presence of strain, and on the right is the calculated orbital magnetization for different values of the strength of the nail order parameter. Okay, and you see that there is indeed a linear dependence on this strain parameter, as you might expect. And so we'll see if this is the last basic point that I can make. The thing that you might want to really zone in on is not so much that there is an orbital magnetization for finite strain, but the question, what is the response coefficient? So what is the orbital piezomagnetic polarizability of a pure altermagnet, and can we calculate that microscopically? So on the left here you have this response equation, but now in the context of the class of models that I'm considering here, and the question is, can we calculate this lambda microscopically? You can do that by taking a general perturbative approach. You just calculate you examine the expression for the orbital magnetization, take the derivative with respect to the field, and then set it to 0 with this general structure after Hamiltonian. Now there is, that seems fairly straightforward, but because this is the orbital magnetization, you have to be a little bit careful that you start with a fully gauge invariant expression. But in the end, what you get when you do that, and this is a fairly general result, is something that that looks maybe a little bit intimidating, but ultimately pretty nice. So there's two pieces to this polarizability. One is what you might call a geometric term. So the ingredients here are P is the projector onto the occupied bands, and Q is the projector onto the unoccupied bands. So this only has these projectors, so this is a geometric term. And the second term here is what you might call an interband term. Okay. So this structure can be compared, if you want, to the magnetoelectric polarizability that drew renewed attention in the context of topological insulators, because in that case there is a topological piece to that polarizability. So this followed a similar script, but in a different context. And when applied to the class of models that I'm talking about here. Again, these two terms take a very simple form, and in particular, the geometric term here, you see here that this is essentially just the Berry curvature of the unstrained pure altermagnet. Okay, and I don't know how much time I have, but I'll just stop at this with this point, is that you can calculate this polarizability for the various models. And so on the left here is the plot for the Lieb lattice model. On the right is the plot for the 2D rutile model. So I can only focus, if I want to consider a linear effect, I can only focus on these two D-wave altermagnets. And I'm plotting it as function of the strength of magnetic order of the nil order parameter. And as you might expect, it, for no nil order, no polarizability. So it starts at 0. And there's a key difference between the two, which is that the different curves represent different strength of spin-orbit coupling. And in the case of the Lieb lattice model, you actually see that the curves go down as you increase spin-orbit coupling. And on the 2D rutile model, the curves go, the polarizability becomes stronger. And this can be traced back to the role that spin-orbit coupling plays in the Lieb lattice model in gapping out the Dirac points and creating concentrated Berry curvature close to where that happens. So when spin-orbit coupling is small, the gap is small, Berry curvature is concentrated, and that's what leads to this effect. How much time do I have? Should I wrap up? It's basically the last point anyway. So the last thing I'll say is, I introduced this model for a G-wave altermagnet in order to talk about a nonlinear piezomagnetic effect. So in a G-wave altermagnet, a linear effect is not allowed, but you can have a nonlinear effect, so generally captured here by this nonlinear response equation. And in the context of this specific model, what you would have to do is introduce two distinct components of strain with xy squared minus y squared symmetry and xy symmetry. And then so if you include these strain components, you can look at the energy bands. Here on the left-hand side is just a plot of the bands. On the right-hand side is the energy difference between the spin up and spin down band that are occupied. And you see here with no strain, it has this nice G-wave symmetric structure. With strain, that of course is broken. And on the right-hand side here is the calculated orbital magnetization for this model. And indeed, you see a quadratic dependence on strain, as you would expect based on symmetry arguments. Okay, and that's pretty much what I wanted to say. So I focused on two things. One is topology from the perspective of symmetry, band structure characteristics, topological numbers, and the simple model of a split quadratic band crossing in the Lieb lattice model, and then examined what consequences that has also for responses that are known to know about things like topology and quantum geometry. So with that, thank you very much. That's all I had.
Thank you, Jorn, for your great talk. And now, time for question, please. Please.
I always have a question. So thank you for the very nice talk, Jorn. Hi, hello.
Hi, yeah, hi.
I was wondering about the symmetries of the piezo-magnetic and the orbital piezo-magnetic response, or the tensor.
Yeah.
Are the symmetries the same? Do those tensors have the same symmetries, or can there be
Yes. Yes, they do have the same symmetry, certainly in the case of spin-orbit coupling. So if you don't have spin-orbit coupling, if you disregard that, then what I think Paul pointed out in his paper, you can actually have a piezomagnetic effect, but then the magnetization can only be spin magnetization because you have to somehow couple the nail vector, which lives in spin space, to something else that lives in spin space. If you don't have spin-orbit coupling, these things are completely equivalent. So the orbital magnetization is something that comes from real space, so you somehow have to couple real and spin space. Yeah.
Thank you.
Okay, more question? Are there a question online?
Yes.
Oh, hi, Daniel.
Hi, Jorn. Thanks for that very nice talk. In your Lieb lattice, when you're looking at your piezomagnetic response and you were taking the limit as spin orbit gets smaller,
Yeah.
what happened when spin orbit went to zero? You had a piezomagnetic response in that case?
Um, uh, yeah, so it's well, what happens there is that you see a signature of the Dirac points. Okay, so that's something that we haven't fully sorted that out yet. But I mean, we can talk about that offline at some point. But that's really where the topology manifests itself, because it's you can take the spin coupling to zero, and the piezomagnetic response will have a piece that remains, but with an ambiguous sign.
I see. Okay.
Okay, so there's the topology of the Dirac points plays a role there.
Okay. Okay, thank you.
Yeah, thank you.
Okay, and it seems no more question. Okay, then thanks again.